So when last we left off, we had talked about how we can use caches to speed up memory access, and we talked about direct mapped caches. And what you might remember is that in a direct mapped cache, every address maps to one specific place in the cache. What I want to do here is demonstrate that sometimes that's a problem, and then also demonstrate how we might solve that. So let's assume that we have an 8 KB cache, that's 8,192 bytes. Our cache line size is 64 bytes, and then a long is 8 bytes. Now let's look at the simple program on the right. We have 3 arrays, each with 1,024 elements. Those elements are longs. I tell you that a long is 8 bytes. So how big is each array? Well, it's 8 kilobytes, right? 1K entries, 8 bytes each, 8 kilobytes. Now there's something interesting about this particular program with this particular cache, and that is because of the way direct mapped caches work. If these arrays are allocated contiguously in memory, which is what C will do, we're going to miss on every single memory access. And that is a disaster. So let's see if we can understand why that's the case. Let's assume that array A starts at address hex 2000. Now, this is the unit where you really want to make sure that you understand your powers of 2, how those map into hex numbers, and then how those hex numbers map into binary numbers, because we're going to be doing that a lot. So 2000 in hex, if we add 8 kilobytes to that, we get 4000. So that's where array B would start. And if we add another 8K, then array C is going to start at 6000. So the question is, what does that imply for the cache? In order to understand that, we need to look at the address and see how we're going to partition up that address into things like the cache tag, the index bits, and the offset. So here is a 32-bit address, and this is how I claim we're going to need to partition it. So let's explain why. The cache lines are 64 bytes. You need 6 bits to access 64 different entries, so the offset is going to be 6 bits. Okay? Now, our cache is 8K. We have 64 bytes per cache line. And so if you divide those 8 kilobytes by those 64 bytes per cache line, what you'll find is that there are 128 cache lines. So now you need to say, how many bits do I need to access 128 cache lines? And the answer is 7. And the other thing that you should notice right away is that, oh, that makes perfect sense, because 7 plus 6 is 13. So we're using 13 bits total to sort of access every element of the cache. And that should be no surprise, because 8 kilobytes requires 13 binary bits. Remember how I said this is where you're going to need to be really comfortable with all your hex and binary conversions? That's the kind of thing you want to be able to check. So if I have 13 bits for the index and offset, I'm going to have 19 bits in the tag so that I have a total of 32 bits. So now let's look at those addresses for arrays A, B, and C. So what I've done is I've taken those addresses and I've represented them in binary. And what I've done is I've crossed out the bits that we're going to use for the offset, because they're important. They'll pick out the right bytes, but I really want to focus on the index bits here. So when we're accessing the first element of this array, then the low order bits will all be zeros. And you'll notice that the index here will also be 0, right? Those 7 bits are 0. So what happens when we access the array sub 1? Well, now the low order bits have changed, because instead of accessing the 8-byte quantity starting at address 2000, we're accessing the 8-byte quantity starting at address 2008. And so that means that we've set 1 bit, but you know what? That's all in the offset. So array sub 0 and array sub 1 will be in the same cache line. Great, no problem. But notice that the element at array sub 1 in both A, B, and C is always in cache line 0 still. And that's what's going to get us in trouble when we start running this program. And this is going to happen no matter what we're accessing in the array. As long as we're accessing these arrays in lockstep, the index bits are going to be the same in all the addresses. So if we want the 8th element in the array, well, we've now done more than, 8, I'm sorry, array sub 8 is the 9th element. So we've accessed all the elements in the first cache line, and now we're going to go on to the next cache line. But notice that we're going to go on to the next cache line in every one of the arrays. And sure enough, this is going to happen throughout the rest of the array, all the way up to the very end, where we've now accessed, we still have all 7 bits of the index are the same in all the addresses. And there's some bits crossed out here that shouldn't be. So let's see how that translates into our program. So here's our little program. And every iteration of the loop, what are we going to do? Well, we're going to read something out of array A. Then we're going to want to read something out of array B. But array A and array B map to the same cache line. So in order to read array B into the cache, we're going to have to kick out array A. So we read that whole cache line in. We only read 8 bytes worth to get the value of array sub I. And before we could do anything else with all those bytes we read into the cache, we're going to kick it out because we're going to bring in the element from array B. But wait, there's more. Once I've read those two and added those values together, now I want to write them into C. So I need to write C. Well, where's that going to live in the cache? Oh, it's in the same cache line. So now I'm going to have to evict what I just read in. So we have this beautiful cache that should let us read one big cache line in and access 8 different long values. But because of our application, every time we read the second value in array A had already been kicked out, and I'm going to take another miss and bring it in. Okay? If that doesn't make sense, sit down and draw pictures and put things in the cache and make sure that that makes sense to you. All right, so now I want to say, how are we going to fix this? And I'm going to step through a couple of different solutions. So hopefully the obvious solution is, well, what if we do what's called a fully associative array? And in a fully associative array, we say, well, a cache line can go in any slot. So maybe I read, the first cache line for A into there, and then I read the first cache line from B there, and C goes there. And now I can access, the next cache line. So because I do that, I get a hit, I take a miss on array sub 0, but then when I access 1, 2, 3, 4, 5, 6, 7, those will all still be in the cache line and those will be hits. And so the same will happen for all my arrays B, C, and for S. So what happens is I'll take for every 8 things I access, I'll take 1 miss, and then the next 7 will be hits, and that's not so bad. Now, it turns out that when we implement caches in software, so like a file system cache or a database cache, we often do use sort of a fully associative arrangement. Unfortunately, implementing fully associative caches is really expensive in hardware. And so it's actually quite rare that we do a fully associative cache in hardware. So instead, in hardware, we're going to make a compromise. And we're going to do something called a set associative cache. So let's use a 2-way set associative cache as an example. What 2-way set associative means is that any address could go into one of 2 places in the cache. So what I've done is I've highlighted this little box that represents what's called a cache set. So all the little boxes still represent individual cache lines. But what we're going to do is we're going to pair those cache lines up and say any address now is going to map into one of 2 locations, the 2 cache lines that comprise the set. So when we read A sub 0 in, it's going to go into cache set 0, and there's 2 slots there. So we can read A in there, and we can read B in there. So now we can take 2 arrays that get mapped to the same place in the cache, and they won't conflict because we have 2 spots for them. Okay, if we had 4 spots, we could have 4 arrays. If we had an 8-way set associative, you could have 8 arrays all there. Okay, so what we're doing is we're saying instead of limiting an address to living in only 1 place in the cache, now it can live in 2. Unfortunately, in this program, that doesn't completely solve our problem, because when our friend C comes in, it needs to go into that same cache set. And that means that we need to get rid of one of A or B. So the process of getting rid of an entry in a cache set is called eviction. And whenever you have a cache, you have some kind of eviction policy. So we're going to spend time later, not in this video, talking about different eviction policies, and we'll try to analyze them and see how they work for different workloads. For now, let's just assume that we can evict either one and it's a random decision, just so we can sort of get the idea of how these associative caches work. So in this case, I happen to say I'm going to evict A and I'm going to put C in my cache. So this feels maybe a little bit better, but depending on that eviction policy, we could still end up doing really terribly. We might do a little bit better. It really depends on the eviction policy. For this particular example, we would be really much, much happier if we had what's called a four-way set associative cache, right? Because in that case, each address can map to one of four places. And so now we can actually keep A, B, C all in the cache all at the same time. And wouldn't that be wonderful? Okay. Now, it's not all wonderful. So skip that slide. Let's look at what happens when we increase the associativity cache. What happens to how we map addresses into cache locations? Okay. So same cache. This was where we had with a direct mapped cache. Recall that we had 6 bits for the offset, 7 for the index, and our tag was 19 bits. Okay. And so I want to focus particularly on the index, right? And remember, the calculation was 8 kilobyte cache, 64 bytes per line, therefore 128 lines, therefore 2 to the 7. But what happens when we make this two-way set associative? Our cache can still hold 128 lines, but we've organized those lines into sets. And a set now has 2 lines. So our index is not picking out a particular line, it's picking out a particular set. So each line can go in 2 places, but we pick out sets now, not lines. So a given address has only half as many sets to choose from, right? We have 2 lines per set. So if we have to pick a set instead of a particular line, we're going to cut that in half. And so what happens here is that when we increase associativity, we're actually decreasing the number of places that the address is going to pick. And therefore, we decrease the number of bits in the index and we increase the number of bits in the tag. So in this case, we used to have 7 bits in the index because we picked a very specific cache line. Now what we're going to do is we're only going to have 6 bits in that tag because we're going to pick a set. And once the address has been used to pick a set, then we're just going, the cache itself is going to decide which entry in that set to put the data in, but it's not going to come directly out of the address. Now, if we reduce the index to 6 bits, the offset plus index only accounts for 12 bits, and so we'd better make the tag bigger by 1 bit, and so the tag becomes 20 bits. Okay, this might sound confusing, and what we'll do is we'll give you lots of practice this week working through it. But what I want to encourage you to do is really think about why you're doing the calculations you're doing, as opposed to sort of just executing a program that you figure out works, like, oh, if I do this, it works. You really want to understand this so that when we throw a new cache configuration at you, you can reason through how you have to partition the bits in the address. Okay, but we'll give you lots of practice doing that.